Hello folks, Rashid here. Hope you're doing well. So in this video, I'm going to give you a recap of what we covered in the last week or week and a half. So it's been officially 2 weeks because the week before I did a couple of videos. So what I want to do today is I'm not going to go into details, so only very quick recap of the things. But the very first slide I have on plan on what I'm planning to cover in this series of videos, which will take some time. Okay, so what we want to do overall is we want to understand and then implement a 32-bit RISC-V, which is the base integer one, which is RV32I. Okay, so we will understand whole RISC, its architecture, its instruction set architecture. Okay, and then we will design and implement in system Verilog. Then once it's implemented, then we will thoroughly verify in system Verilog. And once that is done, we will pick a technology and we will do a complete physical design on it. Synthesize it, place and route it, clock tree synthesis, timing, DRCs, everything, whatever we can do. In this entire effort, my goal will be to prepare an IP that is thoroughly verified, not just a student project. That is important. That's why I think this training will be challenging for me and will be also fun to do. And that's where all of you will get a very good exposure on it. My goal is to you out there, undergrad, master students, or fresh engineers, give you a practical training that you have a good foundation in all these areas. And after that, you can take on complex and advanced topics when you start a job. I'm going to use only open source or free tools because there are many colleges, there are many students out there who don't have access to Synopsys or Cadence tools. So whatever is available with open source, I'm going to use it. Yes, and when it comes to the industry, the job, they're going to use different tools. But I tell you what, if your foundational concepts are good, you know the core theoretical knowledge of every step, then the tool is just a tool. You know what stage next gonna be, what is the goal of that stage, and underlying what are the concept of that stage. Then that stage with open source or that stage with the Synopsys tool or Cadence or any other tool, it doesn't take that much time. I spent my entire career with Synopsys tools, and now I'm with Cadence and using Cadence tool. It didn't take me that long to get better. Of course, when you do in another tape part, you really get into the full flexibility. Well, it's not a flexibility, but you get most comfortable then, right? But I don't think for students, for the type of project we do at student level, for example, this one, I don't think it's a big deal even if we use open source tools. I haven't used them right now, so definitely I need to learn in this training a lot myself. Okay, I am planning, I don't want to overpromise, but I do plan to go into whatever necessary UVM stuff we can cover here so that students also get some overview of that, and not just overview, we're going to use it actually. So I will get some exposure to it and I will give you some exposure to it. Also, during the instruction set architecture initial phase when we are learning it, I'm thinking of we might use Python to model our processor. Okay, so yeah, it's gonna be a lot of practical stuff. It's gonna be fun stuff, but of course it's gonna take time, and if it's gonna take a lot of effort from my side, and I really want to engage serious people there. That's why I have added a membership, but the membership is very reasonable, right? I mean, just two examples. It depends on which country you are, but if you are in US, it's $3. a month, right? This is kind of a very thorough, comprehensive course being done in a year, let's say, $36. But look at the college fees. So it's nothing, right? So, but my goal is to engage the serious students, and this is the bare minimum I can charge, and that's what I charge. So key things, couple of other things for this training is that whenever, as I started right away into architecture, I haven't started with logic design, but wherever those fundamental concepts are gonna come, I will explain those, or I will give a reference of my previous recorded videos or uploaded videos. Say, okay, go watch those ones. But even in the last week, I have explained so many of those fundamental concepts. So what I call it just in time fundamental, whenever they would need to, we will dig deeper. And by the way, before physical design, we will also look into CMOS and how different gates are made, trade-offs on power, performance, and area, PPA numbers, and that sort of stuff. We will look there too. I will do weekly quizzes. By the way, the quiz for the past week is available. I shared the link on the channel post. So go ahead, it's a Google form. You fill it, you will get the correct answer at the end as well. I'm going to share weekly notes. I have shared these one right now on channel page. There is a post, but this is for members only. So whatever I'm going to explain here, the recap of it or whatever I went in detail, I'm going to show every week, because I previously noticed that when I wait for too long, I start forgetting it, and some of my notes are here and there, so it becomes difficult to gather everything. All right. So the book I'm following is really good book. Strongly recommend you to buy this one. And this is the RISC-V edition. I have also the other edition, MIPS edition, which I gone through previously, and a lot of logic design concepts I taught from there. So very nice book. Takes you through a different concept in the right sequence. So I have started with chapter 6 of the edition that I have. It is on architecture. And so I'm going through in a sequence for that, whatever comes in that book. And I'm explaining all the examples that are coming. We will also do most likely chapter number 7. All right, so our blueprint is a RISC-V instruction set architecture. So the chip, I think I have it somewhere here. Maybe I jump on that concept first. That what I was telling that eventually, eventually we will have a board where our processor will be used as a central brain of that board or whatever activity. And we will have some general purpose IOs, we will have some other IOs. Okay, so the users of that chip or users of that board are going to write their code in a high level language, C language, Python, and others. And eventually it will get into the memory and then will be executed and all that. So from users' point of view, they will have a high level language, and then we will talk about that software which converts that into machine language. So you really need to, from user side, what instructions this processor can execute. All those instructions of this RV32I, the base integer. From a user point of view, in order to design a hardware, you need to understand those. You need to understand those specs. And I mentioned a few times during the past week videos too that the reason we are going into assembly language or each instruction understanding of that is because eventually we're going to create a hardware for it. And if you don't understand the specs of it, there's no point in how can you create correct hardware for it, okay? So that's why I'm going to spend a lot of time, probably a couple of months on it, on the architecture level. So understand what is the instruction set architecture. And it's a 32-bit architecture, meaning the address bus to the memory is 32 bits, the data lines are 32 bits. Inside registers are 32 registers, each register is 32 bits. So there's a lot of 32 bit. I mentioned with 32 bits how many numbers you can have. Another concept I mentioned that a user is going to write code in a higher level language. And then the next stage is eventually a lot of time when we want to understand the instruction of the computer, or in this case RISC-V computer, then this assembly is key for us because it gives us a better readability as opposed to reading 0101. So this is too high level, don't understand what's going on at hardware level. This is enough exposure. So typically user writes a program in C, Python, that's a compiler which converts into this code. Then there is an assembler which converts in from assembly language into machine language code. Then machine language code sits in the memory and a different location, and CPU brings from each location one instruction. When the instruction comes, that it fetches that one, of course, it decodes what type of instruction it is, and it executes that and eventually writes that back in. The RISC-V architecture have just load and store when it comes to accessing memory, but a lot of all other instructions operate on the registers inside. This was a generic example. I mentioned that, okay, when we will create hardware for it, we will have like some of these things already connected. We know how data is going to pass, but we will have a lot of cases, write enables, muxes, because we have to select between different things. And these, for example, writes, these enables, different places, these selects lines enable for the register. Those are the ones, those depends on which instruction that is. And the generation logic for those things is called controller, but the rest of the stuff which is fixed are already connected, and we know the what path data is going to take, that is called data path. And so overall is combination is a combination logic and sequential logic. Okay, I said the core concepts on the digital system is, somebody asked me some other lectures, okay, why we do digital. The beauty of the digital is simplifies things with 0-1. We are not dealing with the analog underneath, even though everything in real life is analog, but you're looking into the digital side. It's a higher abstraction level that you're using. But the beauty is when you put things in 0 and 1, you can do a lot of interesting, cool stuff with 0-1s without worrying about the details underneath. And that's why, I mean, this whole thing is digital, so you need to understand this binary system. And I gave you a couple of videos from my previous series. That's this series, and these two videos talk about general binary, decimal to binary, binary to decimal, twos complement, subtraction, addition stuff. Then register is the first topic that we started with. The basic cells are AND, NAND, or inverter. Those are combinational cells. Then we have a sequential cells, latch, flip-flop. Okay, why we need a sequential cell? These are the storage elements, also called sequential. Why these are sequential? Because through them we can give a sequence to a lot of operations. If every operation starts happening at the same time, we cannot put any sequence to it, then you cannot get them you do the useful work. But in order to do the useful work, we need to bring the notion of time sequence, and that's where clock come into action. So on all these storage elements or sequential elements, we have clock connected. Clock is just a 0-1, but we know its cycle time. When we know the cycle time, we know the frequency. And in a flip-flop, which is a register bit, we call it, you have a D, enable, reset, a clock. The beauty is that on every edge of the clock, we move data from input to output. But in order to give it a more control, when we want to, data to move from here on top of the clock, we also have enable. Yeah, when enable is on and clock rise, I then move the data from D to Q. This is also important because we need to reset our computers to a known state. And I gave the concept of what is the given circuit works on which frequency. Registered in RISC-V, we have, though the register I talked above, that was 1 bit, and out of it 32 bit, we connect 32 of these. And we have each of this, you can say take 32, each one is 32 bit, then we have 32 of these, x0 to x31. We also give them a name. These are x0 to 31, I mean total 32. But we also give them some names so that we can refer them for different operations. Some of the registers are very special. For example, this very x0 is, you cannot write into it. It always contains zeros. Even if you try to write onto it, you cannot overwrite those zeros. Okay, having a register with zeros is very beneficial. Then these registers, and these green one I said, these are special one, we'll talk later on. We talked about these storing variables. These general purpose registers are these ones. Then we started looking into add and sub instruction, and took example from the book. We in a high level code is a equal to b plus c, and how actually that goes into assembly. That is important because from assembly we know okay what kind of how things run on our processor. So add, subtract, they take two source operands and one destination. Or what did I say? Yeah, two operands, sources and destination. Two source register, one destination register, right? And then there was another. All the intermediate values are also stored in register. So intermediate where the brackets are, that is done first. Output is put in a register, then all other. So in these ones, we are assuming that these registers already contain those values initialized. But we're not talking about how they come from the memory. All right. So as you have seen that with add and subtract, every time on the right side you have two registers where the operation is happening and output is written in another register. So from that, what we can see that the first thing is that we need to, let's say, we need to put all the registers in a nicely structured together. We cannot let them just spread around the chip. Okay, since we always access them, it's much more important, good, efficient for the timing and the design that you put them together with each other. Or you use a kind of memory like these are 32 bits, 32 total, and each one is 32 bits, so 32 by 32 is the memory. So we will discuss the details of how memory is made and how flip-flop is made during the CMOS part. But the important thing here is, since at one time you need to read two registers, so address 1, address 2 for read data line 1 and 2, and for writing you're into one register. So out of all these combination here, at any time you need to be able to read from two registers and write into two registers. That's where this combination of registers together in more structured form is called register file. This concept I already explained. Then we look into add, subtract, but another couple of instructions are really important. This add I thing is used for two things. When sometime you want to add to another number, which can be part of the instruction, and when it's part of the instruction you use add I, and you can use something like this. Then you can also use this add I instruction, assigning a variable to this variable. Like on this side you can see I is equal to 0, x is equal to this, y is equal to minus 78. Okay, so the number that you actually use here is hold on 1 second, is called immediate. Okay, that number that you have along with the instructions, this number is called immediate. This is a 12-bit number, and in 12-bit we can put also a negative number. When you talk about negative number, there's a 2's complement. Okay, so then I mentioned when you have 2's complement, how you can have a different decimal number represented, and what is the range of the number. Okay, this is interesting. When I was mentioning, okay, there are 0 to 9. Okay, each one has a weight in term of 2. So this is weight of 1 location. These are the numbers in binary, can be 0 or 1, each one of them. Each one has a weight. Okay, and based on the weight and whether it's 1 or 0, that number is calculated. But the important thing here is in 10 bits we can have total, if you add up all of them, we will have 1k. Okay, so if you have 20 bits, then you will have another 1k by 1k, 1 meg, if a 31 gig. And since every number is multiplied by 2, if there are 2 more numbers, so the total in 32 bits, the location we can address is 4 gig. All right, then concept of sign extension, if we have a 5-bit line only and the number is there and it's a negative number with there here 1, and if you want to have an 8-bit line, so how you put, are you going to put 0 or 1? So in sign extension you have to replicate your sign bit, but the number stays the same. Then the last thing we look at actually yesterday was what if you want to assign a 32-bit variable to um, a number to a variable, right? The previous instruction add I did only 12-bit. But another instruction we introduced was LUI, which can put the most significant 20 bits into a register. Then we can add with the lowest um, what are 12 bits, and then that's how we come up with a 32-bit assignment. And I explained this with this an example. There's a little tricky thing there that if the number is negative, then assembler need to do a little bit more effort. Instead of a here, it needs to increment it by 1, so that when you add them, you have a right number, because all these ones are actually -1. All right, so that's a quick recap. That's what we covered. Hope you got an idea of what you have been learning from me over the past week or two. And yeah, I will read through your comments and questions. If there is something, if there's a question that you, something that you haven't understood, then I'll do a separate video on it, and I'll explain that. All right, that's it for now, guys. See you tomorrow.